Everyone, this is Paul Cornelius here, and we're on day 5 of Leetcode Algorithms in JavaScript. A little bit late here locally. It was a very long day of work and running, but wanted to make sure that we worked on the problem we failed on yesterday and we came up with a solution. Because the best thing to do is be persistent when faced with adversity. So a couple of things. Let's kind of go over what happened yesterday and the reason why ultimately we weren't able to come up with an algorithmic solution that passed the test at the end of 1 hour. So reading comprehension is really important. That's kind of an obvious thing to say out loud, but especially when you've got a problem that isn't necessarily the most well-defined. So we ended up coming up with this solution, which is called a immutable, which I call, well, at least I call an immutable solution. That means that we don't modify the original data, we make copies of it and then return a solution that is a copy of the previous data. So this, however, was not what the problem asked for. And in fact, if you read what are called the JS document comments, it explicitly says do not return anything, modify nums in place instead, and that the function actually returns void. So if we had read this JS doc, I wish it had been in this description over here, but sometimes you do have to ask clarifying questions to someone asking you to work on an algorithm. We would have found out they wanted it in place and they wanted no return. So we tried to come up with an in-place algorithm and we kind of waffled a little bit yesterday. So we did glance at a solution and I slept on it just like any person would do when they're faced with a hard problem. Ultimately, what I realized is that there was actually a pretty good hint of what was intended. So if you look at the days, and I know we're way behind right now. In fact, it's probably going to cycle back through again before we're able to get through some of these, especially some of these other ones I've literally never done before in my career, or my personal time for that matter, is that this is under a class of problems called two-pointer. So we've talked about two-pointer on previous streams, but essentially the idea is that you use two variables that have indices, and based on those indices, you traverse a list of numbers and basically do operations. And the intention of this is a little bit of divide and conquer, but it also allows you to do a lot of things what are called in place, which means that you modify the original data, which is mutable, rather than doing immutability. And the advantage of doing this, of course, is that you use less memory because you're allocating less memory than for the subsequent data, which you would have in immutability scenarios. For example, creating additional arrays then to return out of a function. So in immutable land mutable land in place, using two-pointer approach is very powerful. So now that we kind of understand what the approach was and kind of what they're expecting, we can come back, just go back to this tab. So we kind of have an idea of what the approach should be. So let's go ahead and restart the problem. So I'm going to go ahead and this, as sad as this makes me, to be honest, I'm going to go ahead and delete all the code we wrote yesterday because it's not going to be necessary in this case. So what we're going to do instead is we're going to need two things. We're going to need a reverse function. So, okay, I'll say we're not starting from scratch. The concepts of what we learned about yesterday still hold. The key difference is going to be instead of using reverse and doing slice and splice and trying to use all these array methods, we're simply going to run a for loop. We're going to run a while loop with two pointers, which we've kind of done in the previous problems actually. And we're going to reverse portions of the array by calling this reverse function 3 times. The first time we call reverse will be for the front of the list, just like yesterday. Second time will be for the back of the list. And then the back half of the list, basically at whatever k is, like we discussed last time. And then the last time we're going to rotate it around. Now, that being said, I should back off a little bit. We can still use our quotient k hack, right? That's still an applicable. That should still be an applicable shortcut to take, right? Because there's no point in looping through the data multiple times over and over again, right? At the end of the day, if the number k, which is where we want to divide and rotate the data, exceeds the length of the list, then we can just basically take the quotient of the number of rotations by the length of the list itself and get the remainder. And that remainder is basically the resultant place we should rotate without having to go do rotation after rotation after rotation, which is just needless CPU cycles to occur. So if you weren't on the stream yesterday, let's go ahead and kind of show what that would be visually. So in this case, I'm just going to call it remainder k, because I'm sorry, naming's hard, so sometimes naming variables off the cuff is not necessarily great. And it's going to be nums.length modulus, or modulo, I guess it's modulus still in this case, k. And what this should do is for a k that is higher than the length of the list, this should basically let us rotate around and only then have to move the number of places we need to solve the problem. So let's start by proving this out without even working the problem. So we're going to we'll just throw a console log in right here to see what remainder k ends up looking like. And then what we're going to do is, and ignore the first run, it's just going to use the base case. So we'll go to test case here, and we're going to make this greater than the original. So let's keep the target of 3, which is what the test case is looking for. If we count the length of this list, it's 7. So we're going to pick something that is 2 additional rotations through the list, which would be 14. So 14 plus 3 is 17. So we're going to take a number 17. Now, intuitively, we know just by looking at the number of rotations we want to do and the length of the list, if I rotate 1, 2, 3, 4, 5, 6, 7, I'm back to the start. Then 8, 9, 10, 11, 12, 13, 14, I'm back at the start. 15, 16, 17. So if we divide that 17 by the length of the list, which is 7, well, 7 goes into 17 2 times, it's 14, and with a remainder of 3. And that's why we're doing that modulus, because we get the same result by taking the remainder division of this as we would have done just rotating it over and over again for no reason. So, okay, that's kind of a catch-up reminder of why we're doing this from what we discovered yesterday. So we're going to go ahead and minimize the runner for now. We're going to remove this console log, and then we're going to go to the next step. So like I kind of insinuated earlier in the stream, we now need to perform 3 operations on this rotate array. So step 1 is going to be a reverse of the front of the list up to k. And this is, again, for those who are joining late, this is 189 rotate array in Leetcode. Step 2, in this case, is going to be to reverse of the middle, basically k. In this case, I believe it's going to be k plus 1 to the end of the list. And then finally, step 3 is going to be to reverse the entire list. Now, we went over this yesterday in terms of why we're using this approach versus the naive approach, which would be literally to just keep rotating the array over and over again until we get the final result, because this allows us to leverage 2-pointer approach and actually end up doing less iterations for a lower time complexity, which in most algorithms, you're trying to optimize time and space complexity. Now, they're not necessarily exclusive. That is to say, just improving time complexity, you also can always improve space complexity. Sometimes, and in fact, a lot of the time, you're going to be trading off space complexity for potentially time complexity. Not always, but sometimes that's generally the trade-off. You either use more memory or you use more CPU compute. It's generally a trade-off of one or the other. Since this problem is an in-place problem, we are basically going to be trading off CPU in order to keep it in place or to use less memory. So that's the paradigm, and that's kind of the requirement that we've been given to implement this algorithm. All right, that all being said, therefore, what we want to do, and again, we're not going to return anything because it's a void function. Void means no return, is what we would do is we're going to call reverse, which would start at, and since this is at the beginning of the list and arrays of JavaScript are 0 indexed, we start at 0. And then what we want to do is we want to rotate up to the kth position like we discussed yesterday. Okay. The second reverse we're going to do on the list is the back half of the list. So we're going to call our custom reverse again. And this is going to be the index after the middle, or so not the middle, after the rotation point that they want. And then we're going to go to nums.length -1, which is the last index. Now, that being said, I've already made a mistake. Instead of k, what we actually want here is we want the remainder k, because the remainder k represents the subdivided number of rotations we can do. And this is pretty much a pretty cheap optimization, because in the computer down at the metal, taking the modulus of a number by another number is pretty cheap. So this is a good trade-off versus doing a lot of additional computation with pointers. At low enough k's, this probably doesn't help you very much. But if we're thinking from a big O perspective and thinking of a nums that grows exponentially, or even in this case, to the constraints of the problem, which are, where was the constraints? Yeah, to 10 to the fifth. Yeah, this optimization is going to help quite a bit. So hopefully we got it right. We'll find out in a minute, because of course the Leetcode tester doesn't let you get away with anything most of the time. All right, so step 3, final step, is we need to reverse the entire list. So in this case, we're going to reverse the entire list, which would be index 0 to nums.length minus 1. All right, so to be honest, if we implement reverse correctly, our two-pointer approach to reverse, then actually this should be all the code we need from the main action that's occurring in the function. But we need to define reverse. So we're going to create a function. In this case, we're going to call it reverse, and it's going to take basically a start and an end. Now, if I was using TypeScript, which I honestly could flip to, I would type these, but I think first we can stick to standard JavaScript for today. So in this case, let's kind of think about what we're doing here. So the reverse is going to take two indices, and what is the goal of the reverse function? It is to reverse the range of numbers in the nums list or array that we've been given until the pointers effectively either meet or they cross each other. Now, why do I say meet or cross each other? Well, the answer is simple. If I have an odd list, let's say odd length list, let's say 1, 2, 3, and I give index, in which case start and end are 0, index 0, and index 2 respectively, the first step I want to do is I want to reverse the two endpoints. So we're going to get 3, 2, 1. Now, let me ask the next question. What would be the next number to reverse? Well, generally, when we do two pointers, we tend to move inward on itself, right? And generally, it's until the pointers meet or cross. In the case of an odd length list, well, 2 is going to be pointed to by start and stop. Do we need to do an action here? The answer is no, right? Because there's nothing reversed. 2 by itself reversed is 2. So unlike other two-pointer solutions that we've worked previously on this channel, we don't actually care about the less than or equal case. We're simply looking to wait for when start crosses the end pointer, because that tells us as we've worked our way inward, we've finished rotating through the numbers. And to kind of prove this, let's do a length of list 4. So after the first reverse, it would be 4, 2, 3, 1. Second rotation then becomes 4, 3, 2, 1. And at this point, start. So I know I didn't show the start and stop pointers, but at this point, start would be here after 3 rotations, and then stop would be at the index 1. So our condition is complete, and we stop the reverse. So pretty straightforward one to actually implement compared to some of the other ones we've done. So what this function is going to do is we're simply going to perform a while loop here, because a while loop is pretty indicative of what we're trying to do. We want to keep looping while the start pointer is less than the stop pointer, which is what we just kind of described through the two examples of an even and odd list. So while start is less than stop, not equal to, because the equal case requires no additional action, as we also just showed. So while start is less than stop, what we're going to say is, and what are we trying to do here? We're trying to rotate the values at the two positions, or I should say swap. We're trying to swap the values at each position with each other. Now, there are a couple of ways you can do this in JavaScript. You can define two variables, do the swap with a temp, but there's actually kind of a cute hack you can do in JavaScript. I don't know if you, the viewer who are with me, and hello, I see you, have heard of this before, but you can actually do something, I can't remember the name, it's like array something, but you can essentially do something like this. And let me just go ahead and type this out so I can kind of talk through what's happening here. All right, so, and then just to finish this out, after rotation, we want to increment the start pointer by 1, and we want to decrement the stop pointer by 1, because we're going inwards. All right, so what the heck does this crazy code do, Paul, is what you're probably asking. So it's pretty simple. You may already know about this, but for those who are maybe watching the VOD, if anyone watches the VOD, after, essentially what this allows us to do in JavaScript is it says, take this number and basically reassign them in this order instead. So it effectively acts to flip the values. This would be the equivalent of doing something like this. So, defining a temp variable and holding them start, and then doing something along the lines of nums start equals nums end, and then nums end equals temp. So there's two ways. I mean, these are both very valid approaches. So you can either kind of do it like this, which is a traditional approach of swapping given, one temporary variable, or you can kind of use this notation here. I prefer this because this is a little easier. This is more JavaScripty to me, so it's a little easier for me to read. But as you, the viewer, as you're implementing it, I think either approach is perfectly acceptable. So I'm going to erase this now. So what we've done is we've swapped them. We increment start and end, and this will run until start is greater than stop, or conversely, while start is less than stop. Okay, so we've written our reverser function. So let's kind of walk through now the algorithm one last time to kind of understand what's happening here. So I find it best personally to kind of show what the case is and then kind of go through this. Normally I would do this on a whiteboard, but for now I'm just going to do it inside of the IDE, that the sandbox that Leetcode provides, and I think this should be okay enough. So suppose we have a list of 1, 2, 3, 4, 5, and we want to rotate it about the second, about k equals 2. So what should this look like in reality with rotations? What should this list end up being? So if we rotate twice, it should end up being 4, 5, 1, 2, 3. And the reason it looks this way is 5 rotates to 1, so we basically get, it becomes 5, 1, 2, 3, 4, and then it's going to rotate a second time, so we get 4, 5, 1, 2, 3. So that's what we're expecting from the result, okay? So I'm going to take out these kind of intuitive intermediate steps, and let's see if this algorithm ends up arriving at the correct solution. So the first thing we're going to do is run reverse from 0 to remainder k, and in this case, 5 modulus, okay, so here's the first potential mistake. I think we need to be very explicit that if nums.length is greater than or equal to k, then we want to apply the shortcut. Otherwise, it's not going to work, right? Because in this case, this is of length 5, right? So 5 modulus 2 is going to be remainder 1, which is 1 rotation, right? But that's not necessarily, that's not correct, right? Because in the case of, if we do 5 rotations, it should be back to its original place, I think. Let's prove that real quick. So be 5, 1, 2, 3, 4, 4, 5, 1, 2, 3, 3, 4, 5, 1, 2, and then it's going to be 2, 3, 4, 5, 1, and then 1, 2, 3, 4, 5. So that's 5 rotations. So clearly this would get us the wrong answer, because if we don't check the num's length, you're going to rotate once and you're going to get 5, 1, 2, 3, 4, which is not the correct answer. So let's go ahead and add that logic condition. So, and we're going to do it as a ternary, because I think a ternary makes sense in this case. So we're going to say if nums.length is greater than or equal to k, that's the condition. So if this is true, then you're basically going to take the length of the list and modulus it by the number of rotations k. Otherwise, use the value k as is. I believe this should fix that corner condition and make sure that when k is less than the length of the list, we're using k as expected. Okay, so we've taken care of that potential bug. And this is natural, right? Because I'm doing this off the cuff. Like, I didn't write down the solution. So again, as I discussed, you're not going to get these beautiful tutorial videos where everything looks perfect and I look like a genius. I'm no genius. I'm just here learning like the rest of y'all are. So I'm going to show you in real time as I kind of debug my own code as I go through. So I think this will be good, but we'll know in a little bit. All right. So here's our start array, 1, 2, 3, 4, 5 with a rotation of 2. First thing we want to do is we want to reverse it. So we want to reverse from 0 to remainder k. Since k is less than 2, we know remainder k is going to be index 2 in this case. And I've already spotted, nope, that's actually correct. Okay, so in this case, start is going to be 0 and end is going to be 2. So let's see what happens here. So on the first iteration, we are going to swap the number at index 0. And let me put a dashed line here so we make sure we're sane here so we can kind of see what's going on. So we're going to rotate at 0 and then at 2, because 2 is k in this case. So after the first iteration, of reverse, we're going to get 3, 2, 1, 4, 5. And after this, start pointer goes here, and end pointer goes here, because this is kind of the part of the list that we're working on. So like we described, it should occur while start is less than stop. Well, if start equals 1 and stop equals 1, is this condition true anymore? No. So we're done with the reverse. Cool. So we step out of this first function, and now we're going to step into the second reverse, which is going to be from 3, index 3, because 2 plus 1 is 3, to nums.length minus 1 in this case, which will be 4. 0, 1, 2, 3, 4. All right, so let's do it. All right, so in this case, we're going to, so 3, 2, 1 is going to be as is, right? Because that's the front half of the list. And then what we're going to do is, so it's at 3 and 4. Well, in this case, we have one rotation, right? So it's going to become 5, 4, and we're done in this case, right? Because after that point, start will exceed stop, so we're done. Cool. So we're done with step 2. Step 3 is to reverse the entire list. So in this case, we start off with 4 and 3 swap, so it becomes 4, 2, 1, 5, 3. Then we swap the middle two numbers, so it becomes 4, 5, 1, 2, 3. And then we're done, right? Because 1 start and stop are the same index in this case, which is index 2. So we don't reverse 1. That, to me, looks like the correct answer. 2 thumbs up. All right, so let's see. So I think the next step is we feel like our solution is correct. So the next step we want to do is let's run this base case and see if the test runner agrees. And by doing so, we can figure out if just manually stepping through the function, we actually did it correct and we didn't make any logic mistakes. So I'm going to come to this. I'm going to change this to 2 because we want to match the test case to what we walked through. And let's see if the runner agrees with our solution. Well, it would help if your variable names were consistent, wouldn't it? So let's try again. All right, so it says that we're wrong, and it looks like we're off by 1. My most favorite way to fail a problem in JavaScript. All right, so what this tells us is that one of our assumptions when we went through this was wrong. So let's figure out what we did wrong together, okay? All right, so I think the easiest way to debug this would be to use breakpoints, but just for expediency here, what we're going to do is we're going to console log nums after each step, and then kind of see where our assumptions break down. And I'm logging nums because remember, this is an in-place solution, so nums is going to be the source of truth for this problem. There are no other intermediate arrays that we would want to check. All right, so the first one is 2, 1, 3, 4, 5. That seems correct, right? Because in the first case, if you just remember what we did, we flipped these two numbers and then we left this alone. The case that seems incorrect is actually case 2. Because as you can see, it flipped 3 and 5, but what it should have done is actually flipped 4 and 5. So let's go see from the problem where we might have made a mistake. Okay, so remainder k plus 1, this should have been 2 plus 1, which is 3. And then nums.length, in this case, it's 1, 2, 3, 4, 5. That's length 5 minus 1 is 4. So it's very interesting that this did not do what we expected. So let's take a look at what's going on here. Let's just console log the two values we got here and make sure that I've not made a careless mistake, which clearly I have. But let's see if we can figure out what happened here. All right, so k plus 1, interestingly enough, is returning 2. And nums.length minus 1, well, I didn't minus 1 in this case, so sorry, that's a misnomer. That'll be 4. But what it's telling, in this case, what's telling me is that this is not 3. This is coming out to be just 2. So that's interesting. So the question is, what did we miss here? Because this is off. This is essentially off by 1. So what did we do wrong, team? All right, so let's sanity check what remainder k is, because it's saying remainder k is 1, but that can't be possible, right? Because okay, I see my logic bug now. It's very subtle, but let's explain what the bug is. It's up here on line 7, which is probably what you suspected, right? This condition is reversed. So this condition is actually true right now, right? And the reason why is that nums.length is 5 and k is 2. So it's going to apply, so it is applying modulus, which is completely incorrect. What we actually meant to type in this case is k, when k is greater than nums.length minus 1. And that makes sense, right? Because the only time we want to do the little modulus hack is when k exceeds nums.length minus 1, not the other way around. So I am fairly confident after this fix, and in fact I'm so confident I'm going to erase these console logs, we'll see if I regret that in a moment, that the test case will pass after this. And sure enough, it does. All right, so the only other case I would personally suggest testing, and since we know from the constraints that we don't have a case where the list can be empty and k theoretically could be 0. I mean, that k being 0 is probably another corner case we'd want to test. So let's do that. Let's test k equals 0 first because that's easy. And then we'll move on to k greater than the length of the list, which let's pick something like 6. All right, so we'll do 0 first. So line 7 comes first. Is 0 greater than or equal to 5? No. So we take k as is. So step 1, reverse the front of the list up to k. So in this case, it'll be 0 and 0. Well, right off the bat, start is going to equal end. So this while loop won't execute, so nothing happens. Same thing is going to happen here. So 0 plus 1 is 1, and then this becomes nums.length is 1, so 1 minus 1 is 0. So you've got 1 and 0. Well, start is greater than end, nothing's going to happen again. We go to condition 3, reverse the entire list. Well, if I reverse from 0 to 0, I've done no work, right? Now, theoretically, it'll call this, but again, it's the same idea, right? Since start is equal to end, it's not going to run again, so nothing happens. So what I suspect will happen is it's just going to call reverse 3 times, but reverse is actually not going to execute anything. And so in this case, we should get back 1, 2, 3, 4, 5. So let's test the case. And it's wrong. This is why we test our corners. Don't trust yourself. Even if you're really confident, always question yourself, especially when you're on Twitch with an audience. All right, so let's figure out what happened here, y'all. All right, so why are we off by 1? All right, so this is another dreaded off by 1 error, so let's kind of take a look at what's happening. All right, so in the first case, we know that 0 is not greater than or equal to nums.length minus 1. We proved that, right? Because, oh, no we didn't. It's line 7 again. See, we have to be really careful that our optimizations don't actually cause more problems sometimes, because 0, it would be greater than or equal to 1 minus 1, which is 0. So guess what? Condition holds again. So you do 0. In this case, what happens is we would do 1 modulus 0, which is what? 1. Because we're not dividing num's length by anything, so it's going to just return itself. So in this case, for the hack, what we're really looking for probably is only when it's greater than. And that way we don't fall into the 0 corner case. And just for your information, generally, like when you're working an algorithm, I tend to like to check the left side of the constraints because that's generally where a lot of corners occur. At least from my experience of doing some algorithms the past few months, that's where you tend to get in trouble. All right, so I think after that tweak, 0 is not greater than 1 minus 1, which is 0. So we should get k back, and I think this will work again. So let's run the code. Still wrong. Okay. That's interesting. That's not what I expected at all. So we see from the output, it is rotating at once. So let's figure out what it looks like to me. It's going to be hard to know what rotation occurs unless we step through it. So let's step through this. But I do want to see real quick, I want to confirm that remainder k is still 0 right now. Because if it's not 0, then yeah, we still have the same issue. So let's take a look at that to start. Yeah, it's 0. So okay, so perfect. It's working now as expected. So that's not the problem. So let's look at case 1. 0 and 0. So while 0 is less than 0, nothing should happen. So what we would expect after the first reverse is called is that nums should be 1, 2, 3, 4, 5. So let's validate that. And indeed, it is 1, 2, 3, 4, 5. So cool. Step 1 works as expected. Step 2 is going to be 0 plus 1, which is 1, and nums.length minus 1, which is 0. So in this case, start is greater than end, so I would not expect this to trigger. But I'm guessing intuitively right now, step 2 is actually what's firing, and sure enough, it is. So what's happening here, so this is fascinating. Okay, so what's happening is that basically, so everything from index 1 to the end is being rotated in this case. Okay, so that's interesting. Okay, so I see the problem here. When it's 0, this is artificially making this a rotation point of 1, which is 1 after, but in this case, that's not actually what we want. We want the rotation point when k is equal to 0 to remain actually where it is. Otherwise, we're inadvertently going to create a rotation here. So now we need to sit here and think a second about what we can do to get around this. And I'm wondering, let me move my mic here. Sorry, I was just getting a little more comfortable for a sec. It's been a long day. So the question now becomes, how do we handle this scenario where we have a 0k? Because what we don't want to happen here is we don't want to rotate when k is equal to 0 in the second reversal. So I'm just going to take a second here to think, because I don't necessarily have a good answer for us yet. Now I'm wondering if I need to simply, do I take the inverse of this? And what I mean by inverse is what I mean to say, could we do something like nums.length minus 1 minus k? You know, something you might have seen if you've taken mathematics or done any, math recently, something to look at. And essentially what we're trying to do is instead of going left to right, we're moving right to left, right? Because in this case, if it's nums.length minus 1 minus k, k is 0 at this point, then start and stop are the same and we have no rotation, right? So, just for fun and giggles, let's really quickly replace this and actually see if we get the answer we expect. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The issue here, okay, so, interesting. So it's correct, but the problem is that when you get to step 3, you're going to reverse it. Okay, time out. Let's work through this another way. So since we're pretty confident this approach works for any other number other than k, what I would like to do is just do a simple optimization. If k is equal to 0, then just return. Okay, so let's kind of grok through what's going on here. So if we're not supposed to do any rotations, is there any work to do in the problem? The answer is no, right? Because if I don't want to rotate the numbers, then I could just leave the function. There's no work. So that's exactly what this does. If there's no work, we return, which is great because we save ourselves doing 3 operations on the list. So if I put in this simple shortcut, sure enough, we get the right answer. And now to make sure we didn't break anything, we'll set it back to 2, which was our previous case. And we also get the right answer. Okay, so we've done 2 corners. The last one I want to test is when k exceeds the num length, which is the 3rd corner we'd like to test in this case. So let's pick k, since the length of 1, 2, 3, 4, 5 is 5, let's pick 6 as our k. Okay, so I'm going to go ahead and I'm going to pre-fill this into the runner, but we're going to minimize it. Let's come back to the start of our problem. So is 6 equal to 0? Absolutely not. So we passed condition 7. It was a nice try, but it doesn't help us in this case. Next thing we do is we hit line 9, remainder k. So is 6 greater than, and this is actually wrong. Okay. Okay. Hold on a second, everyone. So 6, I'm wondering if I change this condition, whether it actually fixes the 0 condition, although I'm fine with the 0 condition as is. Because what we want to know, because nums.length minus 1 is not the length of the array, right? It's the length of the list, which is exactly what we're looking for, right? So actually, Yeah, I think this fixes it. Bear with me. I have a hunch. Let's go through this hunch. So I'm going to comment out this shortcut. And what I want to see real quick is I want to see if we set this to 0, whether this works. So let's kind of rock through this real quick. So if no, we still need it. I don't know what I'm thinking. I apologize. We do need this still though, because we still need this because we need to essentially make sure that this divides down, right? So in the case of 6 is going to be greater than or equal to 5. So I'm just thinking back. Let's step back again. I apologize. I know we're all over the place tonight. Let's step back one more time. What if k is equal to the length of the list? Let's do that one, and then we'll step into one more, and then we should be done, in my opinion. So if k is equal to 5. So if k, with this addition, is k greater than or equal to num's length? So nums.length is 5, k is 5. This condition is true. If we had the other condition, which I just had, this would have been wrong. I mean, it still would have worked, but it would have been off by 1. And what I mean is that if k is now 4, for example, then you're also going to have this condition hit, but we know that's impossible because we don't want to subdivide down the rotations unless it's at least equal to the length of the list. So that's why we removed that -1. We're truly comparing the length of the list, not the index of the last member of the list, to the number of rotations, k. So in this case, so let's fix our case again. So 5. So is 5 greater than or equal to 5? The answer is yes. And 5 modulus 5 is 0, because 5 divided by 5 is 1 with no remainder. So now we know that k should be 0, which is a big problem. And what that means is that we actually need to do this calculation before, and then instead of checking k, we need to check k here. And the reason why is if we set to 0 after this initial sanity check, what happens? Well, this breaks because of condition 2, which we just talked about. So we want to do this remainder k calculation before we do our first micro-optimization case. Or it's not really a micro-optimization in this case, it's actually necessary for this algorithm to work. So in this case, k is greater than or equal to num's length, so 5 is greater than or equal to 5. So 5 modulus 5 is 1 remainder 0, 0. 0 is equal to 0, so we return. So this case should work, so let's run it.